So we go to our website. Oh, a reminder before I forget, our second midterm would be on July 18. Monday is the same style as the first midterm. So when we go to the chapter on reactor theory, transport and diffusion reactor theory, we covered material on neutron cross sections. Today, what we want to do is develop the theory of the diffusion of neutrons in multiplying media in general. And I hope that the sharing is being done correctly. I had trouble connecting to the internet today. So what we would like to do is derive an equation that describes how neutrons interact with media. And the interesting aspect of neutrons interacting with media is that they follow when they are in thermal equilibrium, not when they are not fast neutrons, when they are in thermal equilibrium with a moderator. And that's what exists in existing power plants that are moderated with water or heavy water or beryllium or graphite. They act in the same way as any diffusion process. Examples of diffusion processes is when you drop some salt into a cup of tea, so in a cup of water, or some sugar even in a cup of tea. And the underlying law in that case is what we call in physical chemistry a Fick's law. So we are going to describe the transport of neutrons in that case according to Fick's law. The idea here is to describe how a neutron interact with the nucleus, scatters of the nucleus with an angle of scattering θ1, and moves a given distance lambda sub s. So that would be the mean free path for scattering. And then it doesn't just interact with one single nucleus, interacts with a second nucleus, and so on, so on. And then when we are interested in the distance, total distance traveled by the neutron, it would be the first mean free path plus the second, plus the mean free path now multiplied into the cosine of the scattering angle, and a third distance that can be described as the mean free path multiplied into the average cosine of the scattering angle. So in fact, you'll find that the distance traveled acts as a transport process. Initially, it's one mean free path, the total distance, and then the mean free path multiplied by the average cosine of θ1, the angle of scattering, plus lambda 3, the square now of the average cosine of the angle of scattering. And that defined for us what we call the mean free path for the reaction. The reaction where the total cross-section now, or total macroscopic transport cross-section, is the absorption cross-section plus the macroscopic scattering cross-section multiplied by 1 minus the mean cosine of the angle of scattering. In that case, as I suggested, the diffusion of neutrons when they are in thermal equilibrium with the medium interact with media in the same way as any solvent in any solute in a solution. Even if you can think about a coloring agent like ink may be dropped in water. So let us try to remind ourselves of Fick's law, which is the physical chemistry law that describes the process of diffusion. And the fascinating thing is that here we have neutrons in terms of the neutron flux that we defined in the previous chapter as n, the density of neutrons in the reactor core or in a beam, multiplied into the average cosine of the scattering, multiplied by the speed of the neutrons. And it represents as a scalar, in that case, the number of neutrons crossing the unit area per second. So the units are neutrons per centimeter squared per second. If the neutrons have a directional property, meaning that they're moving in a given direction, that flux is described as being the current. So you could see here, J here, the current has a vector symbol at its bottom. So the Fick's law describes the relation between how neutrons diffuse in a moderator, in a nuclear reactor, or in a shield against radiation. And it is described as a diffusion process according to Fick's law. In physical chemistry, Fick's law states, quote, if the concentration of a solute in one region is greater than in another solution, the solute diffuses from the region of higher concentration to the region of lower concentration. And this is an observation that's empirical. We all see that in diffusion processes that happen in everyday's life. And the diffusion from the higher concentration to the region of lower concentration depends on the slope of the distribution of the concentration in the solute or the diffusing medium. So in that case, we talk about the gradient or the slope. Think about the gradient in a mountain range. If the gradient is very steep, it's hard to climb it, but it's also easier to come down the gradient. So you find that the neutrons can follow the gradient of the concentration in the reactor in general. All right, so in that case, we can think about three currents in the x direction, a current in the y direction, a current in the z direction, if we use a Cartesian coordinate system. And in fact, with avoiding just the detailed derivation here, we end up using Fick's law as three components of the current, J sub x, J sub y, J sub z. And from the derivation that I have gone through here, it is proportional to the gradient or the slope. And in that case, mathematically, it's the d phi by dx in the x direction, d partial phi by dy in the y direction, and d phi by dz in the z direction. So in fact, the current here is a vector, and the vector has three components. And when we write the three components of a vector with the partial derivative, first partial derivative, or the slope of the graph, this is what we designate as the gradient. And the fact that there are scattering probabilities and total absorption probabilities gives us in Fick's law a minus sign, because the gradient from the center of the reactor core to the outside is going to be a negative slope. And we write it with the symbol of the nabla symbol that you have seen in your calculus classes, that the current is basically minus a constant here, which we call the diffusion coefficient. So the diffusion coefficient is 1/3 the macroscopic scattering cross-section divided into the total cross-section square. So in fact, Fick's law takes a very simple form here, that the current of the neutrons diffusing in a medium follow Fick's law with a diffusion coefficient, but depending on the negative slope, with the slope itself being the gradient of the flux. And this is an interesting relationship here between what we defined as a flux and the current. Diffusion and the neutrons in that case fascinatingly behave like any medium diffusing in any solute diffusing in a diffusing medium. Notice that the gradient operator turns that neutron flux here, which is a scalar quantity, into a vector. Other scalar quantities that we deal with in engineering and in mathematical physics are the temperature. The temperature obviously cannot be a vector. The temperature is a scalar quantity. So when you take the slope of the temperature, the gradient of the temperature, you get the heat flux, and the heat flux in that case is a vector. So when we take the gradient of any scalar quantity, we get a vector. In that case, let's try to remember that the flux is a scalar, whereas the current or the slope of the flux is a vectorial quantity. Diffusion theory does not apply to very close boundaries, close to sources or sinks. If the scattering is anisotropic, it doesn't apply either. So we take advantage of a more advanced transport theory, and we write a different form for the diffusion coefficient as the 1/3 of a transport mean free path that takes into account that average cosine of the angle of scattering. So the diffusion coefficient takes the form of 1 divided into 3 times the macroscopic scattering cross section and multiplying it to 1 minus the average cosine of the angle of scattering that appeared in the first diagram that I discussed. Close to very highly absorbing media, also diffusion theory does not apply. So but it applies to most cases of nuclear reactors and shielding where the neutrons are low in their energy. If the flux is varying with a high rate, also it does not apply close to interfaces between, say, the water coolant and the cladding. We cannot apply diffusion theory. Why are we using diffusion theory and Fick's law, which tells us that the current J as a vector is equal minus D, the diffusion coefficient multiplied into the gradient of the flux? We are using or adopting this concept to derive an equation for the neutron diffusion in any media. And then we'll divide that diffusion equation into 2 types of media. First, media that are non-multiplying, meaning that the neutrons are not multiplied in it. And in that case, that would be the case of a shield. And you'll find that the mathematical description is very similar to linear systems of equations. We call that a source type of a problem. So you have a source of neutrons, and you want to see how they behave in the medium. Why? So that you can shield against neutrons, and it becomes basically a shielding problem, as we'll see in the next chapter. So, however, there is another situation that is described mathematically in a different way when the medium is multiplying, meaning that the neutrons can cause fission. So that's another type of problem. We call it, as we'll proceed, an eigenvalue problem. Why? Because the source term in the non-multiplying medium case, in a multiplying medium, obviously depends on the solution itself. And we'll see in the next chapters that it becomes an eigenvalue problem. So we'll have to deal with 2 types of problems in the way that we are going to analyze how neutrons behave in a medium. One, the non-multiplying medium case, which is what we call a source problem. And that could be the problem, say, of shielding the crew of a spaceship against the neutrons released from in a nuclear reactor, providing power to the spaceship, maybe for a trip to Mars. And so in that case, the problem is what we are going to call a source problem or a shielding problem or a non-multiplying medium problem. When we have sources of neutrons, like in nuclear reactors, the source depends on the solution itself, and it becomes a different type of a mathematical problem, and we are going to call it an eigenvalue problem or a criticality problem. So let us take basically our flux here now in a more formal way. That's a function of space. The R vector here represents X, Y, and Z, and also as a function of time. So this is so it becomes the flux becomes a function of X, Y, and Z, and in time. And let us take a single speed of the neutrons. So let's assume that all the neutrons have a speed v, maybe they are all thermal neutrons running at 2200 meters per second, or the kT neutrons at 0.025 electron volt. So the number density of the neutrons here in the definition of the flux is the one that is a function of space, r here, and of time. All right, so we are going to try to describe the diffusion of neutrons in the same way that we deal in the problem of the transfer of heat in heat transfer, or the transfer of a fluid in fluid mechanics, or the transfer of a current in circuit analysis. So in that case, we are going to take an arbitrary volume, and that volume is simply not relevant to the end results. That's why we call it an arbitrary volume. And then we try to describe the rate of change of the number of neutrons, in that case, d by dt, n of r and t, the number density of neutrons in the that we are considering in the control volume, integrated over the volume v. And we ask ourselves a question: what is that time rate of change of the number of neutrons? It should be equal to the production rate of the neutrons in that volume minus the number of absorptions of the neutrons in the volume minus the net leakage of the neutrons from the surface of the volume. And as I suggested here, the first term is very simple to write. It's d by dt, the rate of change of the neutron density, but we'd like to describe it in terms of the flux. And the flux is equal to nv. So if we divide here by v, then I can write for the flux here nv, and I can take the 1 over v outside the integration term, and it becomes partial d by dt of the flux over the volume v. So that is our first term here, the time rate of change of the number of neutrons in that arbitrary volume v. The production rate is very simple to write. It's an integral over a source term producing a number of neutrons per centimeter cube per second, S of R and T. And we know that to write a rate of a reaction per unit volume, that's what we spent time in the last chapter figuring out. You find that the absorption rate is the macroscopic absorption cross section. We defined it as the product of the number density in the medium, capital N, obtained from Avogadro's law, multiplied into the flux. So here we have now, and of course, we also have a leakage from the surface of the control volume. To estimate the leakage from the volume, we use now the current that comes from Fick's law. Take its normal derivative with respect to the volume and integrate over the surface of the material of that volume right there. And then we can now substitute for these several terms there. And you find that you get an equation over the volume for the rate of change of the flux. Then you have a term that is a source term over the volume minus the absorption rate over the volume. However, to get the leakage from the surface, we take the normal component, that's a dot product with a normal vector to the surface. And it would be an inconvenient type of an equation where we have 3 terms that are integrals over the volume, over the volume, over the volume, but 1 term that's an integral over the surface. So in that case, we seek knowledge from electromagnetics in what is called Gauss's theorem, or in that case, we call it also the divergence theorem. And in that case, that surface integral here is equivalent to the divergence of the current vector over the volume. What is the divergence? It's we write it as the nabla sign of dot product, and this comes from Gauss's theorem from electromagnetics, where the surface integral can be replaced by the divergence of the current. Notice here that when we consider the flux, it's a scalar quantity. And when we take its gradient, we get the vector, the current. Now, the current itself being a vector cannot be acted upon by a gradient operator. We act on it by the divergence operator. We'll see that in detail as we move later on. But that turning of the surface that describes a neutron leakage from the surface into a volume integral allows me to have all the terms in the balance equation for the neutrons in the medium as integral over the volume, over the volume, over the volume, over the volume. So we can combine all those terms together as a single integral over the volume. And since that volume, as we said, is arbitrary, like in applications of, you have seen that in your electromagnetic classes or thermal classes, then we can drop that volume. And that's why we didn't even have a diagram describing the volume, because it's arbitrary. Any volume would work, a cube, a cylinder, a sphere, whatever. So we have now an equation that describes for me the behavior of the neutrons in any medium. And the rate of change in that case is equal to the source term minus the absorptions minus the leakage from the surface. The source term can be a constant. The absorption is in terms of the flux. The rate of change is in terms of the flux, but J here is not the in terms of the flux. So that current here now, as we have shown earlier a few minutes ago, is behaves like according to Fick's law. And we said that the current is minus G, the diffusion coefficient, the gradient of the flux. If we make that substitution, you discover that now I have an equation that is in terms of the flux as a function of space and time. The flux as a function of space and time, the flux as a space and time, and here a constant of the source of the neutrons as a function of space and time. Notice that the leakage from the surface by definition here is a negative term. But when we apply Fick's law, we get another negative term. So negative gives me positive here. So remember, even though it has a positive sign, that term describes a loss of neutrons that are leaking from the surface of the nuclear reactor or the shield. And here we have an equation that we call basically the neutron diffusion equation. It's very hard to solve it as it is. Well, we need boundary conditions because it is a function of space. And you notice now that we have that divergence operator acting on the diffusion coefficient multiplied into the gradient operator. Well, we need to simplify that equation so that we can solve it, and we are going to solve it, I promise you, for some simple cases. If the diffusion coefficient is a constant, we can take it outside the integral. So it becomes and I can bring that term to the left-hand side. So it becomes that 1 over V, the speed of the neutrons, the rate of change of the flux as a function of time now is equal to minus D. I'm taking D as a constant, and then I have the divergence of the gradient. And in calculus, the divergence of the gradient, I'll try to prove it to you in a moment. The divergence of the gradient is, interestingly enough, the nabla square, which is the Laplacian operator. And in that case, the equation becomes that 1 over V, the partial d phi of the flux by dt, minus d del square V, the del square the flux, plus the absorption cross section should be equal or should balance out with the source term. When we took the G as a constant in Fick's law, we ended up with divergence of the gradient, and this is the very famous Laplacian operator. So what do we end up with? We end up with a second order partial You see the partial derivative here, the partial differential equation that is also a function of time. The Laplacian, as you know from your math classes, takes different forms for different coordinate systems. If you use a Cartesian coordinates, del square takes the shape d partial square by dx square plus d partial square by dy square plus d partial square by dz square. And that allows us to form problems that are in the form of cubes or parallelepiped in 3 dimensions. When we deal with cylindrical geometry, if you remember your algebra classes, that the Laplacian takes a different form, 1 over r, d partial by dr, r, d partial by dr. So we have now three coordinates, not x, y, and z, but we have the distance r of the radius of the cylinder, and then we have the polar angle of the cylinder and the cylindrical angle of the cylinder, and then the d squared by dz squared in the z direction. If you have a system that's symmetrical, then of course that term drops out, and we have a simple differential equation in the z coordinate and the r coordinate. And in spherical geometry, we should remember what we learned in our math classes, that's now, instead of 1 over r, it's 1 over r squared d partial by dr, r squared d partial by dr in the radial direction from the center of a sphere. Sine theta, theta here is the polar angle from the z coordinate to the direction of any vector reaching the surface of the sphere. And then we have another angle here, which we call the azimuth or the azimuthal angle. The name comes from the ancient mariners who used the astrolabe to determine where they are on the surface of the Earth. So that determined the latitude, and the sine theta helped them determine the longitude. So you find that the Laplacian takes different forms, and depending on the geometry that we are dealing with. So a cube, a reactor in the shape of a cube, well, implies that we should use the Laplacian in its Cartesian form. A reactor, most reactors are cylindrical in shape. In fact, that implies that we need to use that Laplacian in the cylindrical form. And some reactors are spherical. We'll use that also. Then we use the Laplacian in its spherical form. And the first step in solving really those equations, as we'll try them later on, is to identify the geometry that my shield or my reactor is in, to determine the form of the Laplacian, whether it is Cartesian, cylindrical, or spherical in geometry. In fact, even if we use a computer program, that Laplacian has a general form, and the general form is written like this, that the del should be to the alpha's power, but its del square is 1 over r to the alpha's power, d by dr, r to the alpha's power, d by dr, if there is no dependence on the theta angle and the z coordinate. If you substitute for alpha is 0, you are using Cartesian coordinates. Go back to the equation. If you have alpha is equal to 1, that's for the cylindrical coordinates. And if you take alpha is equal to 2, that is the spherical coordinates. So you can write a computer code, and given what alpha you give to the computer code, it will solve you for a reactor or a shield, or solve the diffusion equation in the Cartesian, cylindrical, or spherical geometry. Now, this equation, again, still in that form, is very difficult to solve this way. So we try to simplify it so that we can reach insight into simple solutions about existing types of reactors. Even if you have a computer to do the job for you, you still need to identify what would be the boundary conditions, what is the geometry, and what are the initial conditions if you have a time-dependent problem. So let's simplify that equation to as a simple level as we can, so that we can find solutions for specific cases of different shapes of shields, non-multiplying media, and reactor configurations when we deal with multiplying media. So how do we do this? The first approximation is to consider a steady state problem. So if you consider a steady state problem, the d partial by dt term is 0, so that is a steady state, and that equation occurs also in the field of electrical engineering when people analyze cable systems and transmission lines. And the first person who solved that equation, of course, in that case, the flux here as a scalar quantity is replaced by another scalar quantity. We mentioned that the heat transfer, similar or analogous form of the equation, would have the temperature as a scalar, del square T, and giving us some indication about another flux quantity, which is the vectorial quantity, the heat flux. But in electrical engineering, it is a voltage. Remember, the voltage does not have any vectorial quantity. So the voltage in electrical engineering becomes a scalar quantity, and then we can take the del square of the voltage in a transmission line, and that is what we call the Helmholtz equation. So fascinating enough is that you replace the voltage is scalar in electrical engineering by phi, the flux. In nuclear engineering, you deal with an analogous problem, and analogies are used in the field of engineering to adopt solutions from one field and adopt them to the solution of problems, analogous problems. They have to be analogs in another field of science or engineering. If we take that Helmholtz equation, we can simplify it further. Let's divide all the terms by d, the diffusion coefficient. So the source term comes to the right-hand side. It becomes minus the source divided into the diffusion coefficient. And then here I have del square phi. It's a second order differential equation. And a partial because of the coordinates x, y, and z, or r theta z, or r theta and phi, the azimuthal angle. And when you get that sigma sub a, the macroscopic absorption cross section, divided into the diffusion coefficient, you get units of 1 over a distance square, because the diffusion coefficient has units of a distance, centimeter, say, and the sigma absorption is centimeter minus 1. So together they have now a distance square. And that distance square here has a physical meaning. When we take the sigma, the diffusion coefficient in centimeters, divide into the macroscopic absorption cross section, the square of that quantity, the d over sigma a, its square root, in fact, would be have a physical meaning, meaning the distance that is traveled by the neutron from the time it is born to the time that it disappears from the system, either through causing fissions maybe, or being absorbed, or leakage from the system. Hence, that quantity d over sigma sub a is what we call the diffusion lengths. And we are going to deal with that equation in the next chapters for different geometries. We'll start with the spherical geometry. It's an easier one to deal with because there have been reactors in the shape of a sphere, but existing reactors are in the shape of cylinders. So we solve it also in the cylindrical geometry, and you can build a reactor in the shape of a cube, like the Chicago Pi #1. In that case, it's in the Cartesian form. So this is a form where you could see here there is no dependence on time. And this is describes the steady state behavior of neutrons in any medium, and it is designated as a Helmholtz equation, giving credit to Mr. Helmholtz analyzing transmission lines in electrical engineering. We can also make another approximation. We can say that if the neutron density and the flux are independent of position, then we find that the initial differential equation becomes only a function of time. So in that case, you drop the del square here and the dependence and the phi dependence, and you get a time-dependent equation. 1 over v d phi by dt is equal to the source minus the absorption rate. This is basically a situation where the equation, the flux itself, only depends on time. It does not depend on space. So we represent the reactor as a point. We call this a problem of point kinetics. It's like even like if you consider the plane flying and detecting it with radar as a point in space, rather than considering the extent of the wings and the rudder and so on. Well, if we are going to solve a second order differential equation here, second order in space means that we have to define two boundary conditions. If you also define a behavior starting at time t equals 0, that would be reactor kinetics. This would be reactor dynamics in the steady state. In that case, you also define an initial condition. But here, it is not a function of time, so we need to define at least two boundary conditions to be able to solve the second order partial differential equation. Partial because del square is partial d squared by dx squared, and plus d partial squared by dy squared plus d partial squared by dz squared. So let's see very quickly what kind of boundary conditions we can use in solving that differential equation. One simple way of assigning boundary condition is that we consider that the reactor or the shield is surrounded by a vacuum. So in that case, we say that the flux at the boundary is equal to 0, and leaving here all the detail, we suggest that the flux leaks a distance, small distance d, which is 2/3 the transport mean free pass. And some people take it as 2/3 the transport mean free pass that we mentioned earlier. They take as that distance that the neutrons leak outside the surface of the reactor as 0.71 that transport mean free pass. So the boundary condition in that case becomes that the flux at the radius of the reactor, the outside radius, plus that small extrapolation distance is 0. And in that case, that presents us with, allows us to have a boundary condition. We notice later that the flux peaks near the center because fissions occur. And from diffusion theory, we simply assume that the neutrons that leak from the surface leak a small distance here in a vacuum, maybe distance d, that we call the extrapolation lengths. And stated mathematically, basically the flux at the radius of the reactor, this point here, plus that extrapolation length is equal to 0, and we can calculate that distance in general. We have another type of boundary conditions, which we call the interface boundary conditions. So if you have two different materials, like a cladding and the coolant on the surface of a fuel, the flux solution at the interface on one side should be equal to the flux on the other side. But also the neutrons are moving from one interface, say from the fuel to the cladding. So in that case, the current also at the interface should be made equal. And in that case, oh, we get two boundary conditions. Other boundary conditions that we have to consider when we solve the equations is that we can get exact mathematical solutions, but they do not make, they don't have a meaning in the real world. And mathematicians, of course, find solutions for us to adopt in different configurations, different situations. And in that case, we use it in solving our problems. But the mathematical solutions sometimes do not apply to real world problems. So that's where the engineers come in, and they identify the situation in the real world and apply the solution, mathematical solution in the real world. So basically, engineers are applied mathematicians in that case. And the physical requirements would tell me that if I have a solution that gives me a flux that is negative or less than zero, well, that does not exist in the real world. So we impose a physical requirement on the solution to the flux that the flux should be larger or equal to zero. And if the solution gives me a negative flux, for instance, we drop it from consideration because, yes, mathematically it may be correct, but it may not meet the real world situation. And we'll see, we'll apply this idea when we solve some the differential equations. Some solutions also that come to us mathematically would imply that the flux can be infinite. Well, you cannot have an infinite number of particles crossing a unit area per unit time. So in that case also, we drop the solution in that case and only take the solution that gives me a non-trivial solution, basically that gives me that the flux is less than infinity in that case. And this is basically the what we want to say about the theory of neutron diffusion. Now, I suggested that what we derived as an equation that describes the behavior of neutrons applies to all situations, but we try to divide it into two cases. One in non-multiplying, for neutron diffusion in non-multiplying media, and one for the diffusion of neutrons in multiplying media. In non-multiplying media, that would be designing a shield, and we are going to design a shield as an example, that will clarify all that theory here. And for multiplying media, that would be the case of reactor theory. And in that case, we'll spend time on both cases. So let's go to the case of a non-multiplying media, meaning that I don't have any fissions or multiplication of the neutrons in the medium. So in that case, the neutrons behave in a way that is different than the situation when they are multiplying and generating new neutrons. When neutrons interact with media, they get absorbed, they scatter, they leak from the surface. But if we have a non-multiplying medium and I have a beam of neutrons with intensity I sub 0 interacting with any piece of material, small that has a thickness x here, let's show it as a target here, call it target, the neutrons can scatter and be lost from the beam or can be absorbed in the material. So you end up on the other side of that target here with a beam that is not I sub 0 anymore, but that has been reduced in magnitude I of x. And here on the other side now you can have a detector that detects for you how much the initial beam intensity has been reduced by placing that target in between the two, because that detector here could be a person that you are trying to shield against neutrons. And we'll see in the health physics or the biological aspects of radiation that, of course, we need to shield ourselves and our coworkers against the effect of neutrons. And if we have spaceships, for instance, we want to shield our astronauts against the effects of space radiation, the solar wind, in fact. Also, our instrumentations like the GPS, the Global Positioning System, communication satellites in space use solid state physics. We need to shield the electronics against space radiation. So if it is neutrons, you'll find something very interesting happens here, that I of x is related to the I sub 0 by the exponential decay law, the same law that we use in the case of radioactive decay, except radioactive decay reduces in intensity as a function of time, whereas in a shield, the intensity of the neutrons is reduced as a function of space. So the attenuation of the neutrons in a shield or a non-multiplying medium follow a very simple attenuation law that I of x, the intensity of the beam after it goes through a thickness x of the material that we are considering, is equal to the initial intensity I sub 0 and a decay as an exponential e to the minus the macroscopic total cross section. That's why we define the macroscopic total cross section. Or I can substitute for the macroscopic total cross section as 1 divided into the mean, the total mean free path. Notice here that in the case of radioactive decay, that was the time here. But we also dealt with the attenuation of gamma rays in matter, and it was the same equation. In fact, also we use the distance in that case, but instead of the macroscopic total cross section for neutrons here, in the case of gamma rays, we had what we call the attenuation coefficient, which had designated as mu, the Greek m mu, instead of the macroscopic total cross section. How do we determine macroscopic total cross sections? We go to the chart of the nuclides for the material that we are considering. We find its macroscopic cross section, multiply into the number density from the modified form of Avogadro's law, where we use the density instead of the mass in estimating the number density in nuclei per centimeter cube of the medium. So this exponential law occurs, of course, here in radioactive decay, in the interaction of gamma rays or electromagnetic radiation with matter, except that the mu, of course, depends on different phenomena. The phenomenon in that case is the content scattering, the pair production, and the photoelectric effects, primarily in the case of gamma radiation. So in that case, X here is the thickness of the shield. Well, as engineers, we want to design those shields. So we're not really interested in what I of X it becomes after we have an intensity I sub 0. What we are interested in is what is the X, the thickness of the shield, given that I want to attenuate it by a factor of that I of X divided into I naught by a factor of 1 million or 1 billion or 10 to the minus 10. That's really what shields are for, reducing the intensity of radiation by many, many, many orders of magnitude. If you are interested in determining what is X, this is designated in mathematical physics as an inverse problem. The same as a problem of radar. You're not really interested in how much your beam of radar has been attenuated after being reflected from a plane. You're interested in determining what is the distance from the radar emitter and the plane. So that's also an inverse problem of mathematical physics if you think about it. Well, another example is in sonar. You're not interested in determining how much your sonar beam has been attenuated by reflection from a submarine if you are on a surface ship, but you are interested, or what is the depth of the water at a given location. What you're interested in is determining what is the distance at which the submarine, or the depth at which the submarine is. So it's another problem of an inverse problem of mathematical physics. Another third possibility that we can think of is the exploration for oil. You explode an explosive, the sound wave reflects from the different layers of petroleum and natural gas, and you want to make a plot, in fact, of the distances that we have at hand. So we really are interested in determining what is X as an inverse problem of mathematical physics. They are very common, and we all deal with them as in the field of engineering. So in that case, we rearrange the equation. We write it as I of X divided into I naught. And that I of X over I naught is a ratio that tells me what is the intensity of the beam after going through a distance x relative to the initial intensity. So we call this the attenuation factor. As I said, it could be 1 millionth, so that becomes 10 to the minus 6, or 1 billionth, that becomes 10 to the minus 9. And we want to solve for x, and we suggested that to get rid of an exponential, we always try to take its natural logarithm. Why that? Is that because the natural logarithm of the exponential is the argument of the exponential itself. So if you take log e of to the minus sigma total x, it gives you minus sigma total x. So let's take the natural logarithm of both sides. So I end up with the minus in that case, because log e to the minus sigma total x gives me minus sigma total x. I switch the sign to the other side, and I'm left with the natural logarithm of I of x divided into I naught. And it's very easy in that case to solve for your x. And this is typical of what we call, again, inverse problems of mathematical physics. So the x, the thickness of the shield, if you want to attenuate the beam of neutrons by the factor I of x over I naught, 10 to minus 6. Notice it's a natural logarithm. It's not the logarithm of the base 10. Is you must have a negative sign here. 1 divided into the macroscopic total cross section of the material, the composition of the shield. It could be just plain water, or it could be concrete, or it could be layers of steel and copper and so on. And that would be the distance traveled, the thickness of the shield that you need to shield against, to reduce the intensity of your radiation by neutrons by that factor. Sometimes that equation is also used to determine what is the cross section. So when we looked at all those graphs in the previous, one of the previous chapters on how the cross sections are tabulated, people have determined what is that cross section. So in that case, what do? They take a beam, they put in material of a thickness x, and that would be n sigma total here, nx. They know the material, so they know the number density, and they figure out what is the attenuation. Oh, and they can determine now the total cross section as a function of energy. All right, so in that case, we have to deal with the this is for the attenuation of neutrons. I'm going to give you a small problem, the same as the problem that we solved in the case of gamma rays attenuation for the attenuation of neutrons in matter. All right, now we are going to deal, as we suggested, with non-multiplying media. So let us look at the equation for non-multiplying media and try to find exact analytical solutions for problems first in non-multiplying media and then in multiplying media. You'll find that when we'll solve the diffusion equation in non-multiplying media, the method of the solution will help us in dealing with multiplying media. But before we start attempting to do this, let us consider some material that will help us in finding analog solutions for these problems. And instead of reinventing mathematics, we are going to find problems in mathematics and physics that apply to the case of our neutrons diffusing in a medium. You probably have seen this material in your Physics 108. So as a reminder, I am going to simply bring it to your attention on how to solve these equations analytically, how to obtain exact analytical solutions in general. The first analog to the problem of neutron diffusion, interestingly enough, comes from mechanical engineering, or from mechanics, if you want to be exact, and that would be the horizontal simple harmonic oscillator if you have a spring. So you have seen that problem before, but I am describing it here in a slightly different way than what you have seen. Consider that you have a mass m on a surface here, horizontal surface attached to a spring, the spring constant being K, and then you yank that mass to the right-hand side, and then observe what happens. What happens is that the spring will try to bring it back. And as it brings it back, the mass is going to compress the spring, but then the spring will push the mass back on the surface, and you'll find that that little mass here is going to oscillate back and forth around the equilibrium position. So the mass is going to literally oscillate. So what is the solution in that case? Well, when you pull it to the right, you are giving it an acceleration x double dot in the positive x direction. But then there are two forces that counter your pulling the mass to the right. One is a force from the spring, and it's proportional to the distance over which you have yanked that mass to the right in the negative direction. So it gets a negative sign with the spring constant K. Also, that surface here may not be a smooth surface, so it may have a friction. So if it has a friction factor, it will also resist your pulling that mass to the right-hand side. And in that case, resistance in terms of friction is not proportional to the distance that you pull the mass out in, but it is proportional to the speed at which you have moved that mass. So it's a force, a resistive force that is proportional to x dot, and the proportionality constant is the frictional factor minus beta. So what is the differential equation for that simple horizontal simple harmonic oscillator? It is that mx double dot is equal to the restoring force of the spring minus kx plus the resistance by the drag of the friction minus beta x dot in that case. So that's a very simple differential equation. Why are we doing this? Because remember, the diffusion equation for neutrons had a second derivative, and here we have a second derivative, and you'll see that the two are analogous, except that our second derivative in our diffusion equation is with respect to space, whereas that x double dot here is a double second derivative with respect to time. So if you find a solution for that differential equation here as a function of time, it is an analog of the equation that we derived for the neutrons, except that time is replaced by space. And the analogy here is time to space, and we don't need to reinvent the wheel. We take the solution for that simple harmonic oscillator and apply it to the case of neutrons by replacing the second derivative in time by the second derivative in space. All right, so what is the solution to that problem? Let us assume that we have an ideal case in which I don't have roughness on that surface. That's a surface that's 100% smooth, so there is no drag or no friction. So that term is dropped from the differential equation, and in that case, mx double dot is equal to minus kx, and x double dot is equal to minus k over m, the mass x. And we know that in that case, the solution to that equation comes from the mathematical physics, as I'll show you in a moment, that x double dot is equal to minus omega square x, or omega square is k over m, the spring constant, stiffness constant, divided into small m. And we know that omega is the square root of k over m, and this is equal to twice pi f, where f is the frequency of the oscillation. You can write that equation also for the simple pendulum, where the kinetic energy at the bottom of the track of the pendulum going back and forth is replaced by the potential energy that it acquires from at the top of its travel. That differential equation comes in from a mechanical analog, as you could see here. But those of us who prefer to use electrical analogs find that it's the same equation can be obtained if you use a tuning circuit in electrical engineering. In that case, you can consider that you have a battery of a voltage V attached to a tuning circuit with a capacitor, capital C, with an inductor, capital L, and a dissipative element as a resistor, capital R. If you have a voltage across a battery here, let's say it's a battery, but let's assume it's a function of time, you'll find that the differential equation depends on the inductance, d squared q over dt squared, where q is a charge that is propagating in the circuit. In the dissipative element, the resistor, it would be R dq by dt, and you recognize dq by dt as being the current. And in the capacitor, you find that it is plus q, the charge over c. So that's a differential equation for that tuning circuit, and that's used in all our electronic equipment, whether it's a TV or a radio or a transmitter of any kind. Remember that energy in the capacitor is stored in the form of an electric field, whereas the energy in the inductor is stored in the form of a magnetic field. When you have a coil and you turn it this way, you create a magnetic field inside the coil. So again, like in the case of the mechanical analog of the oscillating mass on a surface, let us say that we don't have ideally a resistor. Definitely the wire itself offers resistance, but let's just explore it without the resistor. So you'll find that the differential equation becomes simpler with L d squared q by dt squared is equal to minus q over c. Let's bring the L here to this side. It becomes d squared q by dt squared is equal to minus 1 over LC into q. All right, here in that case, we have a circuit that looks, that doesn't have the voltage source here. It doesn't have the resistor. It's only a capacitor and an inductor. And let us say that the capacitor has initially energy stored in the form of an electric field. You'll find that the solution to that very simple differential equation would lead to an oscillatory process. The capacitor will discharge its energy stored in the electric field to the inductor into the form of a magnetic field, and then the energy stored in the magnetic field will discharge itself into the capacitor from a magnetic field into an electric field. The system must oscillate to infinity. So the differential equation is the same as x double dot is equal to minus omega square x, except that the x is replaced by the frequency of oscillation twice pi f as 1 divided into the square root of LC, L the inductance, C the capacitor. Now let's look at that equation number 5. Q double dot is equal to minus omega squared Q. And let us look at the previous equation that we got for the mechanical oscillator. It was x double dot is equal to minus omega squared x. Both those equations lead to an oscillation of the mass on the surface, or the circuit here would start oscillating to infinity. Ideally, of course, this is because you cannot have zero resistance, but ideally it will oscillate between the energy would move from the electric field to the magnetic fields, and from magnetic field to the electrical field. So in general, we have the general form of the second order differential equation. X double dot is equal to minus omega square xt. And we know from mathematics in general that the system oscillating gives us a harmonic solution, meaning that the position of the mass takes a form A cosine omega t plus B sine omega t. And that's why we call it an oscillatory solution or a harmonic solution. Or we can write it in a form that takes the J factor or the I factor in mathematics. Engineers, electrical engineers like to use J for the square root of -1. And we know that cosine omega t plus J sine omega t is equal to E to the plus J omega t in that case. So in that case, we can write it as a solution as A prime E to the plus J omega t plus another constant. Notice that we have two constants of integration because it's a second order differential equation, and you get the second constant E to the minus J omega t. And if you don't believe me, go and take the first derivative of x of t, either in this case or that case, and then take the second derivative x double dot, and you'll see that it does satisfy the differential equation, because this is an equation of an oscillatory system. Now, the interesting aspect of what we are doing is what is the solution if we don't have a negative sign here. The negative sign implies that we have an oscillation. The system is harmonic. It will oscillate between two extremes, and we know that is, in that case, an oscillatory solution. What if the negative sign that we have there is a positive sign? Then we know that the solution is going to be different. Instead of the cosine, we write the cosh here, which is the hyperbolic cosine. And instead of the sine, it becomes the sine, which is a hyperbolic sine. And the hyperbolic cosine is basically can be replaced by e to the plus omega t, and this one can be replaced by e to the minus omega t, with another two different forms of the constants of integration. Why is that? Because e to the plus omega t is the hyperbolic cosine plus the hyperbolic sine, and e to the minus omega t is a hyperbolic cosine minus the hyperbolic sine. If you like, you can go and check these equations in your math courses. In fact, the hyperbolic cosine is the sum of a positive exponential here, a negative exponential, and you take the average of both of them, and the hyperbolic sine is the difference between two exponentials divided into 2. So in that case, in the case of when you have a negative sign in the differential equation here, the solution is harmonic, oscillatory. The system oscillates, and it's fascinating to see later on that this is in fact analogous to a nuclear reactor. The reactor in that case has the same solution for a multiplying medium, in fact, as this equation, where the time is replaced by space r, so x of r in the Laplacian del square. And in the case where the sign is positive, we get a solution that's an exponential growth and exponential decay. And you'll see in a moment that in the case of a multiplying medium, we get the negative sign, and that's why we are going to adopt that solution whenever we deal with it. When you have a negative sign here, the solution becomes harmonic or an oscillatory solution. And when it's positive, and that happens, in fact, in the case of a shield or a non-multiplying medium, you'll find that the sign takes a positive form. All right, so this is just a reminder from physics, because we are not going to reinvent the wheel here. We go back to our diffusion equation, and our ambition is in this chapter to find solutions in non-multiplying media. Remember, non-multiplying medium would mean a shield problem. It would mean also what we call a source problem mathematically. So first, the attenuation of neutrons follow the exponential decay law. If you know the macroscopic transport cross-section, you can determine the thickness of a shield that will reduce the neutron flux in that case by an attenuation factor that you want in your design. Now let's go back to the diffusion equation. If you remember, this is its simple form. The rate of change of the neutron population with respect to time is equal to the source minus the absorption rate minus the leakage from the surface, which is the divergence. I can write the divergence operator here of the neutron current, and we related the neutron current to the neutron flux by Fick's law, so it gave me a second order differential equation. But remember, please remember that the second order here is the divergence of the gradient is in space. That's a space operator. That's d square by dx square plus d square by dy square plus d square by dx square. Whereas in the solutions that we thought for the damped harmonic oscillator and the harmonic oscillator, we suggested that it is as a function of time. But the two equations have the same format. It's second order derivative. This is second order derivative in space, and the simple harmonic oscillator has a second derivative in time. We know the solutions for the simple harmonic oscillation in time. And if we write it and replace the time by the space, then we can get the solution for a nuclear reactor. In that case, notice that it's a second order differential equation, as I'm reminding you here, in space. So this is an analogy. And in fact, at some point, they used what I called analog computers to solve the problem also, other than seeking what we are going to do today as an exact analytical solution. We are going to adopt the spherical geometry because it's easier to derive the equations for the spherical geometry. And then later on, we'll go and deal with the Cartesian and the cylindrical geometry. So let us first start with a non-multiplying medium. And that non-multiplying medium is emitting neutrons with a strength capital S in a non-multiplying medium in space. All right. So if it's a vacuum, it's in space, the neutrons emitted from the source will just move in the same direction as they have been, of course, generated in all directions. And we know in that case that the solution to the flux is very simple. The solution for the flux is the number of neutrons crossing a unit area per unit time, and the area in that case is the area of a sphere at a distance r from the source. So in that case, the solution for the flux in a vacuum, remember, is S over 4 pi r squared neutrons per centimeter squared per second. This is called the inverse square law, because you could see here the flux or the number of neutrons crossing a unit area per unit time is dependent on, inversely dependent on the distance from the source square. And that applies to light, it applies to neutron in our case here today. It applies to sound. When you are far away from the sound, it attenuates according to that inverse square law. So this is in case of a vacuum, all right? It could be a neutron star, and you're looking in cosmology at the neutrons emitted from the neutron star. It could be the neutrons emitted from a nuclear reactor used maybe as a power source for a spaceship. Just watch the movie Space Odyssey 2001. And the neutrons in space just move in the direction that they were born. This process is also called streaming. Streaming relates to the idea of a source of water. Water is coming from a source of water. It keeps moving in the direction where it's coming out. That's why, and or light, this is called the streaming process. But in fact, what we are really interested in is not just a point neutron source in vacuum. We are interested in a neutron source in a diffusing medium. So in that case, if you have a diffusing medium on Earth, the neutrons from the source are going to find molecules of air, for instance, oxygen or nitrogen or carbon dioxide, and they'll scatter or get absorbed. So they undergo a scattering and an absorption process. They do not cause fissions. We are considering here a non-multiplying medium. And we identified that process of diffusion according to Fick's law that had us define a diffusion coefficient, capital D. And when you say you consider also the macroscopic absorption cross-section, we identified for a diffusing medium a diffusion length, capital L. And L squared is D divided into sigma sub A, the macroscopic absorption cross-section. And the differential equation that we have in that case is del squared minus 1 over L squared is equal to minus S over D, the source divided into D. And that's a time-independent equation here. So we are considering the steady state. In solving those differential equations, as I suggested before, we think about the boundary conditions. We think about the form of the Laplacian that applies to the problem. And definitely this is a spherical geometry. So the first step in solving it, as you all know, is identify the source of the Laplacian here. And for spherical geometry, it is 1 over r squared d by dr, r squared d phi by dr. We took a total derivative here because there is no dependence on the theta angle in spherical geometry, the polar angle or the azimuthal angle. So this is the form of the equation that we want to solve for. And it's called the source problem because here it depends on the source on the right-hand side of the equation. That equation looks very much like the simple harmonic oscillator, except the Laplacian here takes a complicated form. So if you want to invoke the solution from the analog solution, we need to make a change of variables that would give me the form x double dot is equal to minus omega square x. Okay, wonderful. Or in fact, when you bring that term to this side and ignore the source for the time being, you'll find that it is a positive term. So it is going to be the exponential growth and decay solution, as you will see in a moment. So first of all, let us consider the homogeneous part of the equation, then deal with the source later on. So in that case, the differential equation we deal with is 1 over r squared d by dr, r squared d phi partial by dr minus 1 over L squared phi of r for the flux. That is for a point source in a spherical geometry in a multiplying, not in a vacuum. To put that Laplacian in the form of the simple harmonic oscillator, we make a change of variables, and the change of variables that mathematicians suggest to us is that we replace the flux, change the variable of the flux as being a new function w of r divided over r. Why? In their analysis of mathematical systems, the mathematicians discovered that when we have spherical geometry, the solution of that second order differential equation always involves the 1 over r, the distance dependence. So let us replace the phi of r in that differential equation by w of r over r. In that term, it's very simple. It becomes minus 1 over L squared w of r over r. In that term, it becomes complicated because I have to replace the d phi by dr by d w of r over r. Now, these are two functions of r. You can consider it as w of r multiplied into 1 over r. And in that case, these are a product of two functions of r. And to get the first derivative, d phi by dr, I have to use the chain rule of differentiation. We are going to do this today in detail, but later on, when we consider any spherical reactors as a multiplying system, we are going to avoid the steps that we are going to go through here and simply adopt that form of the solution. All right, so now I have to write an expression for d phi by dr, change the variables. And the chain rule of differentiation tells me that if I have u, the product of u and v that are both a function of x, we take the first term here, the u, by the dv by dx, plus the second term v here by the du by dx. So that is called the chain rule of differentiation if u and v are functions of x. So what is d phi by dr? It's d by dr, the w of r function, and the 1 over r function. So we take the first term, the w, by the derivative of the second term, which is d by dr 1 over r. As you know, it's minus 1 over r squared. And then you take the second term, 1 over r, by the derivative of the first, dw by dr. That gives me a negative sign here. And in the Laplacian for spherical geometry, I need to multiply that d phi by dr by r squared, and then take its derivative again with respect to r. This is for the spherical geometry Laplacian. So in that case, we multiply by r squared. That first term becomes minus w, and the second term becomes multiplied by r squared divided into r gives you r dw by dr. But we have to be very careful here in that we have canceled here the r squared with the r. So the solution exists for all values of r. This is a simple in mathematics, meaning for all values of r that are not equal to 0. Why is that? We cannot cancel a value of r0 divided into 0 because it is an undetermined quantity in mathematics. So the solution that we'll find here applied to all values of r except at the origin when r is equal to 0. All right, in the Laplacian, we have now a d by dr, that r squared d phi by dr. Now we are faced again with the chain rule of differentiation. So we take d by dr of minus w. Oh, that's simple. That's minus dw by dr right here. But then we have to take the derivative of r dw by dr with respect to r. So we have again the chain rule of differentiation to be applied. So we take the first term r by the derivative of the second. So that gives you d squared w by dr squared plus the derivative of the second term plus the second term dw by dr by the derivative of the first, which is dr by dr, that is 1. Lo and behold, notice here that that term here and that term here cancel, and I'm left with r d squared w by dr squared. The last step is in the Laplacian is that that first term is divided into r squared, as you could see here. So now we take that whole term here divided into r squared. Okay, well, if we do this, you find that r divided into r squared gives you one. Let's see here. If you divide into r squared, you have to be careful again that it's for all values of r not equal to 0. You end up with that Laplacian term 1 over r squared d by dr squared d phi by dr being equal r divided into r squared 1 over r d squared w by dr squared for that term of the Laplacian in spherical geometry. And if we take that value here and substitute it here, I can again cancel the r from both sides. And for all values of r not equal to 0, look what we get here. D squared w by dr squared is equal to plus 1 over L squared w. Oh, wonderful. This is what we spend some time figuring out as the damped oscillator, in the sense that the sign is a positive rather than a negative for the simple harmonic oscillator. Now we know the solution for that w here. We said that in that case, it's an exponential growth and decay or a hyperbolic sign plus a hyperbolic sign. So the solution for the w of our function that we use as a change of variables is a very simple exponential growth function, e to the plus r over L with a constant of integration b, and e to the minus r over L with a constant of integration capital A. So now we have a solution for the help function w of r, and here the solution for phi then would be that help function W of R over R. So we take that solution, divide it into R, and that becomes the solution for the flux for a point source now propagating in a diffusing medium, or we have the L here, the diffusion lengths, where L square is G, the diffusion coefficient divided into the macroscopic absorption cross section. And we can take that solution here and substitute it into the differential equation, and it will satisfy the differential equation for sure. But as engineers, we have to think about determining those two constants of integrations. And just based on physical principles, if you take E to the plus R over L, that solution is exact and correct mathematically. But in the real world, the neutron flux cannot become infinite. We suggested that that's a physical consideration in determining the flux in that case, so that positively increasing exponentially solution is not feasible in the real world. So in that case, we immediately deduce that the B here is equal to 0, giving us a non-practical solution, I should say, even though mathematically it's correct, but because it's not, it cannot happen in nature that we get an infinite number of neutrons from that exponential crossing a unit area per unit time, we immediately deduce that the B here is equal to 0. So the solution for the flux is now A e to the minus R over L divided into R. We determined the B constant of integration. Remember, it was a second order differential equation. So we needed to deduce two constant of integration. So how do we determine the constant A? Now remember that we had ignored the source term on the right-hand side, and that's why we called also diffusion in non-multiplying media. We called it a source problem. We can use the Pillbox method from electromagnetics, surround the source by a small little sphere, and take the current on the surface of the sphere, multiplied by the surface of the sphere, and as R tends to 0, as the pillbox becomes smaller and smaller and smaller, it should be equal to capital S. So in that case, that will help me determine that constant of integration right here, which is the capital A. So we apply that pillbox method to determine A. First, what is the current that we are going to multiply into 4 pi r squared, the surface of the small sphere that shrinks in size to R is equal to 0 at the origin? Well, this is described by Fick's law. So J of R is equal to minus D, the gradient of the flux. So minus D, dphi by dr, and we said that the solution is minus D, g by dr, the solution is A e to the minus R over L over R. Another time today, we are faced with the chain rule of differentiation by separating those two functions, the 1 over R here, and the e to the minus R over L, and it is minus dA, that's equal to the current, and the A comes out of the integration of the derivative sign. We take now the first term, 1 over R, by the derivative of the second. The derivative of e to the minus R over L is e to the minus R over L again, multiplied into the derivative of the argument d by dr, so that gives me minus 1 over L, plus the second term, the e to the minus R over L, multiplied into the derivative, derivative of the first, the derivative of 1 over R is minus 1 over R squared. The terms cancel, as you could see here. The minus and the minus and the minus become a plus, so I have dA here, and then I have 1 over LR e to the minus R over L, plus 1 over R squared e to the minus R over L, and this is the current according to Fick's law. Well, now let us apply the limit here. Let's take the limit as this value of the current tends to 0 and equate it to S. So if we substitute that S in the equation and take the limit of the value of the current, you'll find that as R tends to 0 here, let us first multiply by R squared. So you have the R squared canceling with the R here. I'm left with an R in the numerator, and the R squared here cancels R squared here. So I'm left only with the exponential. Now, as in the limit of R tending to 0, oh, that term turns to 0. And that term here, as e to the minus r over L and R tends to 0, its limit is 1 because the exponential function is equal to 1 at the origin. But we cancel the R squared with the R, so that solution applies only for all values of R not equal to 0, and that should be equal to S. So now I'm left with that term being 1 in the limit, 4 pi GA multiplied into 1, that should be equal to S. And from here, I can solve for A as being S over 4 pi G. And lo and behold, what we have now is we have solved for the two terms in the differential equation for a point source in a medium that is infinite in size, obviously, but it is now a diffusing medium. And the flux becomes, if you substitute for the A constant, first we get a negative exponential e to the minus r over L multiplied into S divided into 4 pi G R. So instead of getting S over 4 pi R squared, the second R here has been replaced by the diffusion coefficient in a diffusing medium. And we have added here the exponential decay in the medium itself. So that is a way of determining the flux in diffusing medium in spherical geometry when the system is non-multiplying. So in that case, I'll show you the shape of that curve. Remember that while we were doing the derivation, we always made it clear that the solution that we get here is not dependent, is not applicable or not valid at the origin. So it does not apply at the origin. We call it a singular point or a singularity, if you want to call it. And notice that it is the same as S over 4 pi R squared in terms of the units, because D has a unit of a distance. So instead of R squared, I have now the diffusion coefficient multiplied into R, and I have that exponential decay that describes that the neutrons are being absorbed. So here is a procedure to estimate that function written in Fortran, and we show the solution for the flux in an infinite medium for the strength of the source being equal to 10 to the 10th power neutrons per second in water, because we have here the diffusion coefficient in water is 0.165 centimeter, and the diffusion lengths in water, neutrons travel in water 2.73 centimeter from the time they're born to the time they're absorbed. So you could tell here that water is a very, very good absorber for neutrons. And if you plot the graph here, you have to be careful if you use the computer code, because you cannot use the value 0. If you use the value 0 in the distance of the flux away from the source, it will give you a fatal error because it becomes basically infinite right here. It's a singularity. So we take a very small number away from the source, and you could see that the strength of the neutron flux decreases as e to the minus r over L divided into r. At a distance of 20 centimeters, you could see that the flux had been reduced to a very significant number. It tells us that water is a very good shield against neutrons. And in fact, since we are talking about shielding here, in the case of gamma radiation, because the attenuation of a beam of gamma rays occurs through the Compton scattering, the pair production, and the photoelectric effect, and some other phenomena too, these are all atomic phenomena. So they depend on the interaction of the gamma photons with the atomic structure. And the attenuation is also exponential. But because the quantum scattering, the pair production, and the photoelectric effects depend on the presence of electrons in the atomic structure, if you want to shield against gamma radiation, you want to use elements or materials that have a very large number of electrons. And in that case, to shield against gamma rays, you use heavy elements like lead, like uranium, like iron. Whereas here, with neutrons, you want to attenuate the neutrons with material that would have the neutron lose as much of its kinetic energy in a collision with the nucleus. So if you want to shield against gamma radiation, you use heavy elements with lots of electrons. If you want to shield against neutrons, you use material that have lots of hydrogen in them. Water is the best material here, but you can use materials that contain hydrogen, like paraffin wax, for instance, would be a good shield against neutrons in general. We'll stop at this, but if you are meeting with the design of more sophisticated systems, you can use water, heavy water, beryllium, or graphite as moderators. In that case, you like to deal with neutrons both as fast neutrons and as thermal neutrons, because fast neutrons still have to be attenuated. I'm going to leave it for you if you meet the design calculation in that case. The solutions become more complicated when you have two media, like the cladding and the moderator next to each other. The solutions, because they are exponential growth and decay, contain lots of the cosine and the hyperbolic sign. I'll leave it also for you if you meet that particular situation in a design calculation. And I'll give you a problem where first you solve for the flux in non-multiplying medium. And I'll ask you to calculate the thickness of a shield made out of water, of graphite. I give you the data for it. And in that case, you learn about how to shield against the effect of neutrons. Now, what to do next is deal with a situation where we have a multiplying medium, and that becomes a topic of great interest all by itself. So we'll leave it for the next lecture, and I'll request that you work on the assignment that will be assigned today to understand what is going on. The class can be dismissed right now, but then I'll stay in the chat room.